Somewhere out past the orbit of everything you've ever personally seen with your own eyes, there's a machine the size of a small car, running on a power source that's been quietly dying since before most of you were born, and in the next few months it's going to cross a line that sounds like science fiction, but is actually just physics doing what physics does. Voyager 1 is about to become so far away that its own voice, the radio signal it sends home to Earth, will take a full day to arrive. Not a delay, not lag, a full day, which means that by the time anyone on this planet actually hears anything Voyager says, the now it was speaking from doesn't exist anymore. It's already history before it's even received. It's a message from a version of the present that has already expired by the time it lands in a dish in California. And here's the part that should genuinely unsettle you, more than any thumbnail exaggeration could. Engineers at NASA are, right now, in 2026, deciding which pieces of this machine's mind get to stay awake and which ones get switched off permanently, because there simply isn't enough electricity left to keep it all running at once. That's not a headline stretch. That's an actual Tuesday at the Jet Propulsion Laboratory. So no, NASA isn't panicking, whatever a thumbnail might have told you to click on. But what they're actually doing, quietly and deliberately, is stranger, slower, and honestly more haunting than panic would ever be. They're rationing the last conscious years of a living memory of human curiosity, one instrument at a time, on purpose, with full knowledge of exactly what's being lost, because doing that is the only way to keep the heart of the thing beating a little longer. Stick with me, because by the end of this, you're going to understand exactly what vanishing into light really means, and I promise you, it's stranger and more beautiful than fiction. I also want to be upfront with you about something, because respecting your intelligence matters more to me than a viral thumbnail. NASA hasn't issued any statement describing itself as being in panic. That's not how mission control operates, and frankly, it's not how careful engineering works either. What's actually happening is quieter, more deliberate, and in a strange way, more impressive than panic would be. Because panic would mean losing control of the situation, and this is the opposite of that. This is control, exercised under brutal constraints, by people who've had years to prepare for exactly this moment. Quick thing before I go any deeper into this, and I promise you it's short, because I know you came here for Voyager, not for me. If you've ever dropped a super thanks on one of these videos, genuinely thank you. It goes straight back into research time and the tools that keep these scripts accurate instead of sensational. And if you ever want a bit more from this channel between uploads, there's a membership link down in the description. Completely optional, zero pressure. Okay, let's get back to the spacecraft. Let's rewind for a second, because you honestly can't understand what's happening to Voyager 1 right now without understanding what it actually is and how absurd its survival has been. This spacecraft launched in September of 1977. Jimmy Carter was in the White House. The first Star Wars movie had been in theaters for about 2 months. Disco was still, unfortunately, thriving. And Voyager 1 was never designed to still be running 49 years later, not by a long shot. Its original mission was almost embarrassingly modest by today's standards. Fly past Jupiter, fly past Saturn, take some pictures, radio the data home, call it a career. A few years of active science, tops, and then a long, quiet drift into obscurity. Instead, it kept going. Engineers used the gravity of those planets like a slingshot, borrowing a little of their momentum with each flyby, picking up speed, and the spacecraft just kept moving outward, past the point where anyone expected it to matter anymore. In 2012, it did something no human-made object had ever done in the entire history of our species. It crossed the heliopause, the boundary where the bubble of charged particles blown outward by our Sun finally gives way to the true interstellar medium, and became the first spacecraft ever to reach genuine interstellar space. Sit with that phrase for a second, because it gets thrown around casually now, but it's not casual at all. Not way out there. Not far from Earth in some vague sense. The actual space between stars. There is a piece of human engineering, built with less computing power than the calculator app sitting unused on your phone right now, currently drifting through the void between our solar system and the next star system over. That's not hype. That's simply, factually, where the machine currently is. Now here's the part that turns this from an impressive footnote into an urgent ticking story. Voyager doesn't have solar panels because out where it is, the sun isn't really the sun anymore. It's just another moderately bright star among thousands, giving off nowhere near enough usable light to power anything electronic. Instead, the spacecraft runs on something called a radioisotope thermoelectric generator, an RTG for short. In plain, unjargony language, there's a chunk of plutonium-238 packed inside it, slowly decaying at a known unstoppable rate, and that decay releases heat. And the heat gets converted into electricity through a set of thermocouples. It's genuinely brilliant engineering. It's the exact same basic principle that's kept both Voyager probes alive for nearly 5 decades without a single recharge, without a single trip to any kind of cosmic gas station. But here's the catch, and it's a catch baked directly into the laws of physics. Not some oversight or design flaw anyone at NASA is responsible for. Radioactive decay does not stop. It does not pause for maintenance. It does not negotiate. Every single year, without exception, without mercy, Voyager 1 loses roughly 4 watts of usable power. 4 watts. That's less electricity than a dim nightlight pulls from an outlet. And it happens every year, forever, with no way to refuel the source, no way to send a repair crew 15 billion miles to swap out a battery, no way to do anything except watch the number get smaller on a spreadsheet and plan carefully around it. Before we go further, let's actually put some real numbers on this, because I think scale is exactly where most of these videos fail you and where this channel tries to do better. Voyager 1 is currently more than 15 billion miles from Earth. Try to picture that for a second. Not 15 million, 15 billion. If you drove a car at highway speed, non-stop, 24 hours a day, never stopping for gas or sleep, it would take you something like 28,000 years to cover that distance. Voyager itself is moving at roughly 38,000 miles per hour relative to the Sun, which sounds unbelievably fast until you realize that even at that speed, radio waves traveling at the actual speed of light still take over 22 hours, one direction, just to reach it. Now here's the number that should really land for you. When Voyager first launched in 1977, that same signal took only about 8 minutes to reach it, roughly the same amount of time it takes sunlight to reach Earth. Over 49 years, that 8-minute conversation has slowly stretched into a 22-hour one. And it keeps stretching a little more every single day until it eventually crosses that full 24-hour, one light day mark later this year. That's not a metaphor. That's a literal, measurable fact about the growing gap between us and the farthest thing humanity has ever built. And it's genuinely worth pausing on before we move to the harder part of this story. So think, for a moment, about what that actually means if you're one of the engineers currently working this mission. You're not really managing a spacecraft in the traditional sense anymore. You're managing a slowly shrinking budget of electricity for a machine that, at this point, is older than most of the people currently keeping it alive. And when that budget finally runs too thin, something has to give. This isn't a new problem, by the way. This slow, deliberate process has been unfolding for decades already, largely out of the public eye. Back in 1980, the photopolarimeter, an instrument used to study reflected and polarized light, was the first thing switched off, partly because it had degraded anyway once the primary planetary flybys were finished. In 2007, the plasma science instrument went dark for good. In February of 2025, the Cosmic Ray Subsystem, a suite of 3 telescopes that had spent decades tracking high-energy particles streaming in from the Sun and from deep within the galaxy, was powered down specifically to conserve electricity. And then, on April 17th of this year, engineers at JPL sent the actual command to power down the low-energy charged particles experiment, the instrument that had been quietly, faithfully measuring the structure of interstellar space almost continuously since the spacecraft launched in 1977. Nearly 49 years of essentially uninterrupted data collection, and then, deliberately, on purpose, silence. Not because the instrument had broken down, because simply keeping it powered on would have cost more electricity than the mission could realistically afford to spend. And it's worth knowing what that particular instrument was actually doing, because it wasn't some minor footnote. The low-energy charged particles experiment had a small motor built into it that rotated the sensor, letting it scan in multiple directions to map out the structure of the interstellar medium around the spacecraft. And interestingly, that little half-watt motor was left running even after the rest of the instrument went dark, which means, in theory, it could still be woken back up someday if the power situation ever improves. Nothing out here is quite as final as it sounds. Even off doesn't always mean gone forever. And that small detail alone tells you something about how carefully every part of this spacecraft was designed, decades before anyone could have known just how long it would need to keep working. And I want you to genuinely sit with that for a second, because I think it might be the most human part of this entire story. These aren't failures in any real sense. These are choices made by people under pressure with incomplete time to deliberate. Someone at NASA had to look at a list of scientific instruments that were still functioning perfectly, still capable of teaching us things absolutely no one else in human history has ever known, and decide which of them get switched off so the spacecraft itself can keep surviving a little longer. Kareem Badaruddin, the Voyager mission manager at JPL, put it about as honestly as I've ever heard an engineer put anything on the record. Shutting down a working, healthy science instrument is not anybody's preference, but given the situation, it's the best option actually available to them. Read between the lines on that quote for a second, because there's a lot packed into it. That's not the language of panic, and it's definitely not the language of a crisis spiraling out of control. That's the language of grief, carefully managed, with a job that still has to get done, regardless of how anyone feels about it. But here's where this story genuinely earns its drama, because there was a real moment, not a manufactured one, where this whole delicate balancing act very nearly fell apart in an instant. On February 27th of this year, Voyager 1 was going through a completely routine roll maneuver, the kind of small positioning adjustment the spacecraft has performed thousands of times before, without a single hitch over decades of operation. And during that particular maneuver, its power level unexpectedly dropped, not gradually and predictably, the way the 4 watt per year decline normally unfolds, suddenly and sharper than anyone anticipated. Engineers on the ground, watching the telemetry come in, realized that if that drop had continued even a little further, it would have tripped something called the undervoltage fault protection system, a kind of last resort safety mechanism built directly into the spacecraft's original design decades ago by people who never in their wildest imagination expected it might actually get triggered for real 49 years into an already impossibly long mission. Here's exactly what that system does, and why its near activation was such a genuinely tense moment for the team. If Voyager's power level ever drops below a critical, hard-coded threshold, the spacecraft is programmed to automatically shut down components entirely on its own, without waiting for any instructions from Earth, purely to protect itself from a total cascading systems failure. Sounds smart in theory, right? It absolutely is. Except think carefully about the distance involved here. A radio signal traveling from Earth takes over 22 hours, one way, just to reach Voyager 1 at its current position. So if the spacecraft trips this fault protection system and begins autonomously shutting things down on its own initiative, the engineers back on the ground can't simply flip a switch and correct it in real time, the way you might reboot a router in your living room. They'd have to compose a command, send it, wait almost a full day for it to physically arrive, and then wait nearly another full day just to find out whether or not it actually worked. Recovering from an autonomous fault trip out there isn't a quick 5-minute reboot. It's a lengthy, uncertain, nerve-wracking process, and it carries genuine risks of accidentally making the underlying problem worse. That, right there, is the closest this mission has actually come to a real crisis in recent memory. Not a fabricated NASA panic headline designed purely for clicks, but a genuine, brief warning shot from a nearly 50-year-old machine, quietly telling its creators that the margins are getting thinner than anyone would honestly like to admit out loud. And here's what makes it even more unnerving if you actually stop and think about the engineering culture behind it. This fault protection system was written into Voyager's software back in the 1970s, using programming logic that predates almost every piece of technology you interact with daily, on hardware with less memory than a single low-resolution photo on your phone. Nobody who wrote that code was thinking about the year 2026. They were thinking about protecting a spacecraft during a handful of planetary flybys that were supposed to be over within a decade. That it's still functioning correctly, still doing exactly what it was designed to do, nearly half a century and several unplanned decades later, says something remarkable about the people who built it in the first place, working with slide rules and punch cards instead of the tools we take for granted now. So, after all of these careful, deliberate shutdowns, what's actually still left running on board? Voyager 1 is currently down to just 2 functioning science instruments out of an original suite of 10. One listens to plasma waves, essentially allowing it to hear the electrically charged particle environment surrounding the spacecraft, translating raw physical phenomena into something almost resembling sound. The other measures magnetic fields directly, mapping out the invisible structure of the space Voyager is currently passing through. Space that quite literally no other human-made object has ever physically touched before it. Just 2 instruments, and they're still working beautifully, still transmitting genuine, first-of-its-kind data from a region of the universe we have no other practical way of studying up close. The plasma wave instrument in particular has already given scientists something nobody expected: actual measurements of the density of the interstellar medium itself, the incredibly thin soup of gas and charged particles drifting between star systems, something that had only ever been theorized about before Voyager physically pushed through it and started listening. Every week that these last 2 instruments stay alive is another week of data about a part of the universe that no telescope on Earth, no matter how powerful, could ever directly sample from this far away. Because you can theorize about the interstellar medium from a lab bench all you want, but there's simply no substitute for a physical instrument actually sitting inside it, taking real measurements in real time. That's the actual stakes here, quietly sitting underneath all the power budget spreadsheets and shutdown commands. And it's why every single watt saved elsewhere on the spacecraft matters so much to the people running this mission. That's the nuance that gets completely flattened by a headline like NASA in panic. The panic framing tricks you into assuming something is spiraling out of control. What's actually happening is closer to the opposite of that. Something is going remarkably right, on borrowed time, purely because of careful, deliberate, painful sacrifice made by people who refuse to give up early. Now, here's where this whole story gets a little bit hopeful, because NASA isn't simply accepting the slow, inevitable fate without a fight. They're actively trying something bold to buy more precious time. It's an initiative the mission team has nicknamed, only half-jokingly, the Big Bang. The core idea is to replace several of the spacecraft's older, more power-hungry components all at once, swapping them out for newer, far more efficient alternatives, essentially performing delicate open-heart surgery on a machine 15 billion miles from the nearest repair shop, using nothing but carefully timed radio commands and an almost unbelievable amount of patience. And because this is such a genuinely high-stakes maneuver, one wrong move away from disaster, they're deliberately not testing it on Voyager 1 first. They're testing it on Voyager 2, its twin, which happens to have slightly more spare power available and sits somewhat closer to Earth, making it the comparatively lower risk candidate for this kind of experimental procedure. If it works as intended, the same fix could eventually be rolled out to Voyager 1 as well, potentially extending its working scientific life by years it otherwise simply wouldn't have. Tests were scheduled for May and June of this year. Just think, for a second, about the sheer audacity baked into that plan, attempting to essentially rewire the internal electronics of a spacecraft that launched during the disco era, all from a control room on a planet it physically left behind before a lot of your own parents were even born. And if it goes wrong, there's no do-over. There's no second spacecraft to send out to fix it, no way to physically inspect the damage. Nothing but telemetry and educated guesswork from nearly 15 billion miles away. Every single command sent to either Voyager has to be triple-checked, simulated and re-simulated on identical hardware here on Earth before anyone dares transmit it for real, because a single mistake could end the mission instantly, with zero chance of recovery. That's the quiet tension sitting underneath every one of these decisions, and it's exactly why the team tests on Voyager 2 first. Better to risk the more resilient twin than the one already living closer to the edge. Let's circle back to that opening hook now, because I promised you a real explanation, not just a dramatic tease, and I meant that. Sometime this year, Voyager 1 will officially cross the 1 light day threshold, the exact point at which it becomes so unimaginably far from Earth that light itself, the single fastest thing that exists anywhere in the universe, takes a full 24 hours just to travel the distance separating the spacecraft from us. When you hear a phrase like vanish into light, please don't picture something mystical or explosive or dramatic in a cinematic sense. Picture this instead, because it's far stranger and far more real. Every single signal Voyager sends home is already, by definition, a message from the past by the time we actually receive it. As that communication gap stretches past a full day, Voyager doesn't disappear in some sudden dramatic flash. It slowly recedes into the delay itself. It becomes less like a spacecraft we're in active, live contact with, and more like starlight arriving from a star that might genuinely no longer exist by the time we see it. Information reaching us from a now that technically doesn't exist anymore by the moment it finally lands in a receiving dish here on Earth. That's not a manufactured NASA panic headline. That's simply one of the strangest, most quietly beautiful consequences of the finite speed of light, happening in real time to a machine that human beings built with their own hands. And honestly, I think that's what makes this whole story worth 15 or 20 minutes of your attention instead of just a quick scroll past a misleading headline. This was never a disaster story to begin with. It's a story about limits. The hard limit of plutonium decay, the hard limit of light speed itself, the hard limit of what a piece of 1970s engineering was ever realistically supposed to survive, and about a group of human beings quietly refusing to let those limits win without putting up a real fight. Every single instrument they choose to turn off is a small, deliberate act of grief, performed in service of keeping something larger alive just a little bit longer. Suzanne Dodd, the Voyager project manager, once called these two probes deep space rock stars, and honestly, I don't think that's an exaggeration in the slightest. If the team doesn't manage this shrinking power budget with real precision, both spacecraft could realistically have only a few more months of usable power left before an official end of mission has to be declared. Instead, because of careful, deliberate choices like the ones we just walked through together, there's a genuine, credible chance that at least one instrument on at least one Voyager keeps transmitting data well into the 2030s. Not because the underlying physics got any easier, because the people managing this mission simply refuse to stop trying. And there's one more piece of this whole picture that I think tends to get buried underneath all the technical detail, which is what these two spacecraft are actually physically carrying with them. Bolted to the outside of each Voyager is a golden record, an actual physical engraved disc containing sounds and images meant to represent all of Earth to whatever or whoever might one day happen to find it drifting through the dark. There are greetings recorded in dozens of different human languages. There's music sampled from cultures spanning the entire planet. There's the recorded sound of a mother's heartbeat, of wind moving through trees, of distant thunder, of a kiss. There's a diagram etched directly into the metal cover showing the location of our sun relative to a set of well-known pulsars. Essentially a treasure map in case whoever finds it someday wants to know exactly where this thing came from. It was assembled by a small committee led by Carl Sagan in an era with no internet, no digital archives, working almost entirely by hand to decide what fragments of an entire species and an entire planet deserved to survive into forever. They had one shot at it, no revisions once it launched, and they got remarkably close to getting it right. Whether or not another scientific instrument ever functions again, whether or not this ambitious Big Bang upgrade actually works as planned, whether or not that undervoltage fault protection system ever gets fully triggered for real one day, that golden record just keeps traveling regardless. Long after the very last watt of power from that slowly decaying plutonium finally runs completely dry, long after every single remaining instrument goes silent for good, Voyager 1 keeps drifting onward, quietly carrying humanity's message outward, forever, into a universe that none of us alive today will ever personally get to see for ourselves. That's not really a machine vanishing into darkness at all when you think about it properly. If anything, it's closer to the exact opposite. It's a small, deliberate, carefully chosen piece of light that we sent outward into the void on purpose decades ago, and it's still going, right now, while you're watching this. So here's what I actually want you to genuinely sit with once this video ends and you move on to whatever comes next in your feed. Somewhere out there, right now, this exact moment, a 49-year-old machine is quietly deciding, with help from people who weren't even born when it first launched off this planet, how to make the absolute most of the very little power it has left to work with. It isn't panicking. It isn't vanishing in some sudden dramatic instant, no matter what a thumbnail might have implied to get you here. It's fading, slowly, deliberately, entirely on its own terms, while still doing genuine science that no other object in the entire history of our species has ever been positioned to do. If that doesn't make you want to step outside tonight and think seriously about just how astonishingly far 4 measly watts a year can actually carry something, I honestly don't know what will. If this kind of story, the real science quietly hiding underneath the sensational headlines, is the kind of thing you'd like more of from this channel, go ahead and subscribe now, because there's a genuine follow-up video already coming on exactly what that golden record contains, and why the choices people made about it back in 1977 still matter enormously today. And if you want to actually see it for yourself, in a way you technically can. On a clear night with genuinely dark skies, away from city lights, you can look up toward the constellation Ophiuchus, roughly in the direction Voyager 1 has been heading this entire time, and know that somewhere out past everything visible to your naked eye, past even what most telescopes could ever hope to resolve, there's a small, fading, deliberately rationed piece of human ambition, still transmitting, still listening, still going. You won't see it, nobody ever will again, not with eyes alone. But it's there, and it's still working, and it's still ours. Until next time, take care of yourselves out there. Keep asking the kinds of questions that don't have easy answers, and I'll see you in the next one.